Então, o giro da Terra em torno do Sol está sujeito a uma força central, e é por isso que a Terra gira em torno do Sol no mesmo plano. Isso vai dar origem às leis de Kepler do movimento planetário, que não está dentro do escopo da ementa desse curso. Mas é importante você saber que a força central não quer dizer que o objeto em movimento circular será atraído para o centro. A força central varia a direção do vetor velocidade tangencial. Essa força central, ou força radial, é o produto da inércia vezes a aceleração centrípeta, que é a velocidade tangencial ao quadrado sobre r na direção radial. Na verdade, o correto seria colocar um sinal menos aqui, porque essa força radial é voltada para o centro atrativo. Removendo a força centrípeta, o objeto vai se mover em linha reta, a partir da tangente da trajetória circular. Vamos ver aqui um experimento realizado por um astronauta que está na Estação Espacial Internacional a respeito do movimento circular e da aceleração centrípeta.
Welcome to Astro Academy Principia, featuring astronaut Tim Peake on board the International Space Station, Sophie Allen on the ground in the experiment room, and myself, Anu Ojar, at the National Space Academy. Welcome to the Kinetic Centrifuge facility in Farnborough. This enormous accelerator is used by scientists and engineers to simulate the effects of extreme G-forces on the human body. And the focus of this film is the physics of circular motion, the role that forces have in keeping objects moving in circular paths. Now, Newton's first law of motion means that the plastic ball in Tim's demonstration wants to keep moving in a straight line at a constant speed.
Okay, this next demonstration is for the ball and string. So I've got about 15 centimeters of string there, and I'm just going to rotate it round.
But because Tim's holding on to the string, he's applying a tension force through the string onto the ball. And from the ball's point of view, this tension force is directed towards the center of the ball's circular path. The effect of the tension force, which is at right angles to the ball's instantaneous direction of travel, is to deflect the ball away from the straight line path it wants to follow. And as long as Tim keeps applying the right tension, then, whatever the orientation, the ball will keep following its circular orbit with a velocity that's constantly changing, because although its speed is constant, its direction is changing. The ball is constantly accelerating. But if Tim releases the string, the tension collapses. Now the ball moves at a constant speed and in the direction it was moving at the moment that the tension force disappeared, drifting in a straight line right across the Columbus module. In Tim's demonstration, tension was playing the role of a centripetal or center-directed force. For any object to move in a circular path, some overall or resultant force must be acting in this way on it. And what that force is depends on the situation that we're studying. For the International Space Station, or ISS, moving at nearly 8 kilometers every second, it's the gravitational force of the whole Earth on the ISS itself that's providing the necessary centripetal force, directed towards the center of the Earth. But for a proton beam being accelerated in CERN's Large Hadron Collider along its 27-kilometer circumference, it's the forces produced by the motion of the protons through the hyperstrong magnetic fields of over 1,600 superconducting magnets that keep these high-energy charged particles on the correct circular trajectory. So whenever we have circular motion, some combination of real forces must be acting on the object to produce an overall center-directed or centripetal force. And that includes motion in vertical circles.
First of all, to do this, you need to be really careful or you'll get absolutely soaked. Here I have a cup full of water, which I'm letting hang freely. Now I'm going to swing it back and forth higher and higher until it's almost vertical. And as long as I keep the cup swinging with a circular velocity above a certain minimum value, then I'll stay completely dry. How was that possible?
Because the space station and all of its contents, including me and my kit, seems to be weightless, this means that the only apparent force acting on the ball, once I set it rolling, is the reaction or contact force from the track on the ball, and that will always be at 90 degrees to the surface of the track. This contact force is providing the centripetal force needed. And even when the ball slows down due to air resistance, as long as it's still moving, we have enough contact force to maintain the circular path, whatever the orientation of the loop.
And I'm having to hold a very steady hand now so that I don't impart any velocity onto that ball. It's starting to bounce off the track. It's barely keeping to the edges of the loop. Any minute now it's going to come off the track and go off in its own direction.
It's only when the ball loses contact with the track that the contact force disappears.
And there it goes.
So why are things different back on Earth?
We're going to analyse the process using this loop-the-loop track and a marble. Ignoring the effects of air resistance, there are two main forces acting on the ball as it rolls around the track. The effect of gravity, its weight, which will always be directed downwards, and the reaction, or contact force, of the track on the ball itself, which will always be directed inwards and at 90 degrees to the surface of the track. It's the combination of these two forces that provides the centripetal force to keep the ball moving in a circular path. So let's consider our analysis at 3 different points. Here, the ball is moving with maximum velocity. Gravity is directed downwards and the contact force upwards. The resultant force on the ball must provide the centripetal force necessary to move the ball in a vertical circle. And here, that resultant force will be the contact force, which is upwards, minus the gravitational force, which is downwards. The ball continues, climbing in the loop to this point and reducing in speed. Here, gravity is still pointing downwards, but the contact force is at 90 degrees to the track surface, directed towards the centre of the circle. So here, gravity isn't contributing at all to the centripetal force. The only contribution towards the centre of the circle is from the contact force. And as the ball continues to climb the loop, it slows down still further. Now, we know that there's a critical minimum velocity that the ball must have at the top of the loop in order to not fall off the track, but to complete the vertical circle. How can we find that minimum velocity? Well, at the top of the track, both gravity and the contact force of the track on the ball are acting downwards, towards the centre of the circle. And so both are contributing to provide the centripetal force required to keep it moving along the track. The minimum velocity needed to complete the loop is when the ball is moving so slowly here that it's hardly touching the surface at all, at which point the contact force drops to 0. If this happens, then the gravitational force on the ball is providing all of the necessary centripetal force. And when the centripetal force is equal to the gravitational force on the ball, i.e. its weight, we can show that the minimum velocity is given by this equation. And the same equation will apply to the cup of water.
Here, in kinetics horizontal centrifuge, it's the angular velocity of the arm that we're controlling. And this means that we can create contact forces on a pilot in the cabin that simulate the sorts of forces that astronauts re-entering the Earth's atmosphere may experience, up to 9 times their normal weight. Now, the data from these types of acceleration experiments have found life-saving applications in many other areas, including aviation safety. But as long as human beings continue to explore the space environment, the centrifuge will remain an essential part of training astronauts for the rigours of the acceleration and deceleration they experience, both on their journeys into space and in returning them safely back to Earth.
que estamos falando sobre força central, dentro desse tópico de princípio da conservação do momento angular, é interessante ressaltar que o trabalho realizado pela força centrípeta é nulo. Consideramos que o trabalho, devido a uma força constante, é igual ao produto escalar entre a força e o deslocamento dessa força, o deslocamento do ponto de aplicação da força. Então suponha que a força que estamos tratando é uma força radial, uma força central como a força centrípeta. No movimento circular, essa força centrípeta passou de uma posição inicial para uma posição final. Então o ponto de aplicação da força deslocou-se por um deslocamento ΔR, que é numericamente igual ao arco de circunferência dessa trajetória. Esse deslocamento ΔR ele tem a direção da velocidade tangencial, isto é, a velocidade tangencial é igual a ΔR sobre ΔT. Então o produto escalar dessa força radial, que é uma força centrípeta, será m, velocidade tangencial quadrado sobre r, na direção radial. Esse vetor radial r aqui, ele é paralelo ao raio da trajetória, ele aponta para fora do raio da trajetória e é perpendicular à trajetória. Então observe que esse vetor radial R chapéu, que não foi desenhado aqui nessa figura, ele é perpendicular ao deslocamento radial. Então o produto escalar de dois vetores perpendiculares entre si é igual a zero. Pelo teorema trabalho e energia cinética, se o trabalho é igual a zero, a variação da energia cinética é igual a zero. Então a energia cinética final é igual à energia cinética inicial, ou, em outras palavras, a rapidez final é igual à rapidez inicial. Isso mostra que a magnitude da velocidade da partícula é constante. Há somente uma variação da direção do vetor velocidade, que é provocado pela força centrípeta.